Hey everyone, welcome back to another video about A-level physics past papers. Today we're going to talk about the paper 1-3 variant from the May June 2025 series. Just like in the last videos, before we jump into the paper, something to show you some resources that will prove very helpful while solving these papers. Uh, This is AS definitions and formulae. As you can see, these will contain all the relevant definitions, formulae, and major key points, not all key points. Then we have frequently examined questions. Frequently examined questions currently they are from P2, but we are working to include some very frequently examined questions from paper 1 also. Then we have derivations. Derivations, these ones are which are required by the syllabus. Some of them which are also not required. I've also included that also just as a learning exercise. And some of these come in the exams also, such as you might see for the resistors in series and resistors in parallel. They are very frequently examined. Then we have A2 frequently examined questions. This is structured differently. We Along with the syllabus points, we have the corresponding questions and their marking schemes aligned answers. And on the right hand side, you will see years. There will be some questions where you will see a lot of years. That means those are very frequently examined questions. Then, just like for the AS, we have the definitions and formulae. Similarly, graphs for A2 are more important because students struggle with their field and the potential graphs of electric fields and gravitational fields. So we have included them as along with the other important graphs also. Furthermore, we have important derivations for A2 also. Again, the ones that are listed in the syllabus, the ones that come in the exams frequently also, and some of them in between also just as a learning exercise. And last but not the least, the paper 5 planning question. This Although this is straightforward, but students sometimes miss a few things that result in loss of marks. So we have created a sort of checklist for this, which is based on the syllabus itself, the syllabus requirement, the marking scheme, and the examiner reports. And we have included some solved examples also. Now, as you may wonder if you're going to be able to fit all of this in the space given. You might not, but this is here to show you what details you can include. So actually, you might be able to fit most of it, but these are here to show you how grammatically correct sentences you can use instead of short phrases, but with details. All right, moving into the paper. Okay, so question number 1. What represents a vector quantity? We know vector quantity is a type of physical quantity that is represented by a magnitude, that means a numerical magnitude, numerical size, and direction. This direction is supposed to be a direction of change in space, okay, not direction of change in time or something else. If we look at the options, 1 Newton upwards, this is a direction in space. But 2 kg decrease, this is a change in mass. This is a direction of change in mass. No. Direction of change in temperature? No. Direction of change in time? No. Direction of change in space? This is correct. Okay. What is a reasonable estimate of the current in an electric kettle that is used? Now, electric kettle we use in our homes, it uses a lot of amperes. So microamperes definitely not, milliamperes not. It's not a small LED that consumes that less current, and it's not even that big that consumes a lot of ampere. That would lead to a lot of units consumed. 8 amperes is a reasonable amount. Which statement about errors in measurements is correct? Okay. Accurate set of measurements always has a small random error. Precise set of measurements always has a small systematic error. Okay. Uh, both of these are incorrect because the accurate set of measurements have a small systematic error. Actually, the accurate should not have any error at all. They should not have any systematic error at all. But still, a precise precision is related with this, how close the measurements are. A random error can, so both of these are incorrect basically. They are not related to each other. The random error is reduced by taking an average of several measurements. This is correct. So systematic error can be reduced, can only be reduced by figuring out what the error is. If it's a zero error, you reduce the zero error. If it's a problem in your formula, a problem in the measuring process, you have to change that. You have to correct that. Otherwise, the consistent bias will remain. A systematic error creates a random set of measurements spread out about true value. This is a definition about the random error, actually. So not a systematic error. So again, this is incorrect. So C is correct. Moving on. A sample of material has a cross-sectional area A and L. The temperatures on the two sides of the sample are T1 and T2. Thermal energy is transferred through the sample in time T. These quantities are related by where K is a constant. What are the SI base units of K? Okay, so thermal energy Q is in joules. This is in joules. Time is in seconds. A is in meters squared. L is meters. And T1 minus T2, that is in kelvins, because this is temperature, right? So K, the formula for K would be Q over T times by L over A divided by T1 minus T2. So units wise, this would be joules over second, meter over meter squared over 1 over Kelvin. So simplifying further, we have joules per second per meter per Kelvin. Furthermore, joules, I just remembered, joules needs to be converted also. The joules is a unit of work done, force times by mass. So force is kg, force times by displacement, kg meters per second squared times by meters. This becomes meters squared basically. So furthermore, this can be represented as kg meters squared second squared times by second minus 1 meter minus 1 Kelvin minus 1. So this simplifies to kg meter. 2 minus 1 is just 1. Also minus 2 minus 1 minus 3, and Kelvin minus 1. So which one is this? Uh, yeah, this one, B. All right, moving on. The graph shows the variation of velocity with time t of an object moving in a straight line. At t is equal to 0, the displacement of the object is 0. What is the displacement of the object at t is equal to 20 seconds? Right, okay, so we need to figure out, see, at this point, the velocity has become 0. What does this mean? Velocity becoming 0 means it's a it's a turning point. It's turning. At some point, at somewhere, it's turning from one direction to another. However, the gradient going from positive to negative just simply means that first it was accelerating, now it was decelerating. Now, 20 is over here. So we need to figure out what is the displacement of your object. So net displacement, this area added with this area. That would be distance. For net displacement, we need to do the plus of this area and minus this area. So the first 16 seconds, 0 to 16 seconds, this is half times by 16 times by height, which is 3. So that would be 8 times by 3, 24. Then we have 16 to 20. This is half times by 4. And this is 1.5, 3 by 2. So 2 times by 2, 2 times by 2, sorry, 2 times by 1 is 2. So this is just 3. So net displacement would be actually 24 minus 3, which is 21. Okay, moving on. The Science Museum designs an experiment to show the fall of a feather in a vertical glass vacuum tube. The time of fall from the rest in the vacuum is close to 0.5 seconds. Which length of the tube is required? Okay, so the fall time has nothing to do with the mass of the feather. So we already know that because the acceleration in that vacuum will not change. Uh, since it's falling from rest, we can use 2as is equal to b squared. And what else we can use? We can use s is equal to half at squared. We could also use v is equal to at because u in all of them is 0. However, we don't know the final speed. So we don't know the final speed. So that means we cannot use these. This is the only equation that makes sense over here. So because we need to find out length, we know acceleration, we know time. So s would be equal to half times by 9.81 times by 0.5 squared. So 0.5 times by 9.81 times by 0.5 squared. So 1.22 roughly. This length would be sufficient, close to 2 significant figures. Right, moving on. 2 coins are projected from a horizontal table at the same initial speed u. Coin X is projected horizontally. Coin Y is projected upwards at an angle 30 degrees to the horizontal. Both coins hit the horizontal ground without bouncing. Assume the air resistance on each coin is negligible. Which statement about the motion of the coins is correct. Both coins hit the ground with the same speed. Now, this one is correct, but let's explain why. So this is the top of the table, and this is the actual ground where they are landed. So what's going on over here is that this will have this trajectory, and this will carry on somewhat like this. Somewhat like this. This is oh, never mind. Okay, I hope you get the gist of this. So since at this level, they share the same speed. That means when this ball, when the coin reaches the same level as the original starting point, it will have the same speed q original as before, which further means that both of them will undergo similar accelerations in their vertical components as soon as just before they hit the ground. So the net change in their velocities would be the same. So they're going to hit the ground with the same speed. So both coins travel the same vertical distance? No, they're traveling the same vertical net displacement, but not the same distance. Coin Y has a smaller vertical acceleration. They both have the same vertical acceleration. So that's easy. Okay, two spheres are released from rest at equal heights above the ground. Both spheres reach terminal velocity. One sphere has a larger density than the other sphere. Both spheres have equal volumes. Which statement is correct about both spheres? Which statement is correct while both spheres are at terminal velocity? Okay. Now, we know the mechanism of objects attaining terminal velocity. So the downward force, most often weight, uh, is balanced by the resistive force or the frictional force or the drag force, whatever we want to call it. So when the sum of forces becomes zero, the acceleration becomes zero, that's constant velocity is called terminal velocity. Now, this resistive force, since we're talking about spherical objects, although it's not part of the syllabus, but we are familiar with Stokes' law, which represents the drag force. Again, this is not part of the syllabus. I'm not saying that, but it can be used to explain the drag force on spherical objects. This n over here is not n. This is viscosity. This is eta viscosity. R is the radius of spherical object. V is the velocity, and 6 pi is just 6 pi. So as you can see over here, while everything else is constant, this part over here is constant. The drag force is directly proportional to radius and velocity. Okay, so this means that when you have one sphere that has a larger density, and since they have equal volumes, one of them will have a smaller radius and the other one will have a larger radius. Both of them will have the same acceleration initially, because again mg acceleration would be the same since they're just falling from rest. So they will undergo the same acceleration initially, but the change in speed for them will be different. The one that has a larger diameter will slow down faster. the one with the larger diameter, it will slow faster. That means it will achieve terminal velocity greater at a greater rate because the drag force will catch up very quickly. Whereas the smaller one, it will take a little bit of time. However, this does not mean that they have the same terminal velocity, their weights are the same. We don't know that. They have equal volumes, larger density. So obviously that means that masses are different. Resultant forces on the spheres are equal. This is the only thing that is true for both of them. That is true for both of them. Resultant force is 0 for both of them because they're both falling at terminal velocity. Now, what do we know about objects in terminal velocity? The only thing we need to know is that why it happens when the weight of the falling object is balanced by the resistive force, drag force. So in that case, we know that when the drag force becomes equal to the weight, the sum of forces becomes 0, acceleration becomes 0. So whatever the velocity is not, that will be the terminal velocity. Furthermore, something to notice, one of the spheres has a larger density, but both have equal volumes, which means the one with the larger density will have a will have a larger mass because they have equal volumes. They have the same volume. Larger density would mean more mass. Now, which statement is correct while both spheres are at terminal velocity? Drag forces on the spheres are equal. No. Why? Because although the drag force equation, again, this is not part of the syllabus. Sorry, not again. This is not part of the syllabus, but you might see this in past papers or something. This is just a constant, but this is the radius of the spherical object and this is the velocity of the spherical object. Since the radii are the same, this means that the velocity is going to be the deciding factor. One of them has a larger mass, which means it will have a larger weight, which means it will take more time for the drag force to catch up to the size of the weight. So the drag forces for both of them while they're falling at terminal velocity is not going to be the same. Velocities of the spheres are equal, no, also for the same reason, because for one of them it's going to take a longer. That means more speed will be attained. Weights of the spheres are equal, absolutely not. We have already decided that. We have already determined that B is the only answer that makes sense. That is true. Okay. Which statement defines force? We already know that's the rate of change of momentum, which is again a very important definition. Again, you will find this definition multiple places. Force is the rate of change of momentum. Force is the rate of change of momentum. Okay, both places. But let's see what is given over here. When force acts on a body that is free to move, force is the product of the mass of the body and its acceleration. Okay. When a force acts on a body that is free to move, force is the rate of change of momentum of the body. This is correct. When a force acts on a body that is free to move, force is the work done by the force, definitely not. Force is the, no. So B is this. Okay. Four forces, all in the same plane, act on an object. What could describe the motion of the object? Okay, so let's add the so 12 is canceling out the 12, 20 is canceling out the 20. That means Wait a second. Right. So there is no resultant force acting over here. So the 12 is canceling out the 20, 20 is canceling out the 20. So the net force is 0. However, none of the suggests that. However, we know the Newton's first law. Newton's first law deals with when there is no resultant force. So again, to show you this again, Newton's first law of motion states that a body continues at rest or constant velocity unless acted upon by external force, which means it's not accelerating. It is not. See, it is moving with decreasing speed would mean decelerating, so no. It is moving with increasing momentum, no, because resultant force is 0. It is moving in a straight line. This is correct because the body is inertia, basically. Okay. A nucleus collides with a stationary nucleus in a vacuum. The diagram shows the parts of the nuclei before and after the collision. Okay. No other particles are involved. Which diagram is not possible? Uh, Parts of the nuclei before and after. Okay, so one of them is stationary. Sorry. Okay. Which diagram is not possible? Which diagram is not possible? So since both of these nuclei is a very positively charged, so we will expect a very high change in momentum. So we know that the momentum before and momentum after are conserved, and that also involves the perpendicular motion also, not just the parallel motion. So for one nucleus, so one nucleus has u this way, some non-zero, and the other nucleus has velocity 0. So which means that the momentum after has to be conserved with the momentum before. So this makes sense because there is the perpendicular part also. So this shows that the momentum is conserved. Again, perpendicular part showing that there is other aspects of momentum conservation also. Same with here. This is the only thing that does not make any sense because they're both going in the same direction. Like although they're both moving towards the right, but their perpendicular direction is going towards downwards. So this does not make any sense. Since the momentum is conserved, the uh, the perpendicular directions which their directions perpendicular to the original direction should have been opposite. So this is the only thing that's not possible. Okay, sorry, my bad. A non-uniform bar PQ has length 50 centimeter and a weight 200 newtons. A block of weight 400 newton is attached to the top of the bar at its center. The bar rests on horizontal ground. The vertical force 360 newtons is now exerted on a bar at NQ and is sufficient to lift the NQ from the ground. NQ from the ground. Okay. What is the distance from the center of the gravity of the bar to end P? Okay. So since P is acting like the pivot, this is 400 Newton. And when it says it is just sufficient, that means the object is still in equilibrium, but it will just lift it right ahead, or it's very close to just lifting it. Finally, when it says non-uniform, this means that the center of gravity is not at the center, which means the block is not sitting at the center of gravity. The center of gravity is somewhere else. Somewhere else. Let's assume that this is this over here. Let's give this x over here, and the weight is 200 meters. Okay. Now, since it is just sufficient to lift the NQ from the ground, so let's still assume the equilibrium because it is just sufficient. So moment clockwise equals to anti-clockwise. So 360 times by 50 equals to 200 times by x plus 400 times by 50. Sorry, 25. So 360 times by 50, that is 18,000. This is 200x, and this is 400 times by 25, 10,000. So 200x would be 18,000 minus 10,000, only 8,000. So x would be 80 over 2, which is 40 centimeters, which means 0.40 meters. What is the definition of density, mass per unit volume? Simple, not mass per cubic meters, something like that. No, that's not correct. Okay, a block is in equilibrium on a slope. Equilibrium means that the triangle of forces is a closed loop. That means all the arrows are in a circle. Which vector triangle represents the three forces acting on the block? So you see, this is going this way, but this is going this way, so that's not correct. A also not circle, it should be a circular loop. This is correct. This is also not correct. A measuring cylinder contains 80 centimeter cube of a liquid. The pressure due to the liquid at the 60 centimeter cube mark is 1200 pascals. What is the pressure due to the liquid at the base of the measuring cylinder? So this means that we have a measuring cylinder. If we had 60 centimeter cube mark, the pressure would be 1200 pascals. So this is about the height, right? If we add 20 centimeter cube more, what would be the pressure now? Sorry, my bad. I misunderstood the question. It says due to the liquid at this mark. So at this mark, the pressure due to the liquid at this mark is 1200. So this means that we need to figure out what's the pressure acting at the base of this. So if from the 80 at this point it's 1200, so this was just a difference of 20. So we have 3 times more. So 20 further, it's 40, another 1200. Again, this would be another 1200. At 0, this would be another 1200. So 1200 plus 1200 plus 1200, that is 4800. D. Okay. 4 identical uniform blocks are spread on a table. Each block has a mass m and thickness h. The acceleration of free fall is g. How much work is done on the blocks? in stacking them on top of one another. So for one of them, there is no change because you're stacking the three on top of them. So let's say, for example, if this is the first one, this is the second one, and this is the third one. For the first one, the change in height is h. So change in, let's say, height is h. For the second one, the change in height is 2 times by h. Furthermore, for the third one, the change in height is 3 times by h. Okay, so the total change in potential energy for which is going to be equal to the work done. For the first block, 0. For the second block, mgh. For the second block, sorry, for the third block, this is this one. We numbered it as 2. So mg times by 2 h, and then mg times by 3h. So 3h plus 2h plus h, that is just 6 mgh. That is this. An electric motor uses 1.7 kilowatts of power when operating normally. The efficiency of the motor is 53%. What is the useful power output of the motor? This is easy. We just have to multiply that because the efficiency is power output divided by power input, and this is in percentage basically. So efficiency is in percentage. So power output would just be efficiency times by power input. So power output would be 0.53 times by 1.7. You can keep it as kilowatts, it doesn't matter. 1.7, that is 0.901. And this would be the B part, right? A ball is released from rest and falls vertically to the ground. The kinetic energy Ek of the ball varies as the height h of the ball above the ground changes. Air resistance is negligible. Which graph shows the variation of Ek with h? Okay, now Ek is half m v squared. If we know how v is changing, we can figure out everything. It's releasing from rest. So v is basically a t. So v is changing. Oh wait, sorry. We need it with h. Sorry, we need it with h. So that would be 2as is equal to v squared. So if you replace v squared with 2as over here, so Ek would be equal to half m 2ah. 2 get cancelled. However, what that just simply means is that Ek is directly proportional to height, or the variation of height, basically. So as the height of the above the ball changes, that means height is actually decreasing. This is not the same thing. Sorry, this is not the same thing. This was the displacement. This was the displacement. So the displacement is increasing, the height on the other hand is decreasing. So this is not going to be the case. This is going to be the case because as height is because as height increases, height is increasing. Sorry, height is decreasing. This way, kinetic energy is increasing. This is the correct one. Not this one again, because there's a difference between displacement and what we mean about the height. Because height is decreasing, displacement is increasing. Okay. An object traveling with a speed of 10 meters per second has a kinetic energy of 1500 joules. The speed of the object is increased to 40 meters per second. What is the new kinetic energy of the object? Okay, so notice that the mass is constant, obviously. So EK half m v squared. So the half m part is constant. So this means that EK over v squared is equal to constant, right? So E1 over V1 squared equals to E2 over V2 squared. So we need to find out the E2 basically. So E2 would be V2 squared over V1 squared times by E1. So new speed is 40 squared, old speed was 10, and old kinetic energy was 1500. So 40 squared, which is actually 1600, divided by 10 squared, 100, so that would be 16, times by 1500, that is 24,000. So C part. What are the units of stress, strain, and Young modulus? Strain is unitless. Young modulus is stress over strain. Stress has pascals. Strain is unitless or dimensionless. So E, the Young modulus, will have the same units as the stress, which is pascals. So Pascal, no unit Pascal, that is D. Okay, moving on. The force extension graph for a metal wire is shown. Each quantity is represented by the area under the graph, that is the elastic energy or strain energy. So let's see. All the work done on the wire. Okay, so power transfer, definitely not. Temperature, no. Time taken, no. Work done on the wire, which is the elastic potential energy, strain energy, whatever we want to call it. A wire of length L naught is attached to at one end at a fixed point. A tensile force is applied to the other end so the wire extends and has a new length L1. What is the strain of the wire? So strain basically is just the change, sorry, it's just the change in length over the original length. So the change in length is L1 minus L naught. Original length is L naught. So let's see which one of them it is. So this is L1 over L naught minus L naught over L naught, which is can also be represented as 1. So L naught, L1 over L naught minus 1, minus 1. This is A. Okay, moving on. A wire of length L is stretched to determine its limit of proportionality. The graph shows the variation of extension x with the force F applied to the wire. Limit of proportionality is shown by the point P on the graph. The experiment is repeated with another wire of length 2L but of the same material and the same diameter as the first wire. Which point of the graph shows the limit of proportionality for the new wire? Okay, what this means is there are three things to notice over here. Another wire of another wire of length 2L but of the same material, same diameter. And yeah, so basically the same thing. So what goes on now further is that same material means Young modulus is the same. So if E is the same, that means stress over strain relationship, that is the same. Diameter same, that means stress would also be the same. Furthermore, obviously, what's left is that means strain will also be the same. Now, if strain over here, let's call it x over the original length L, if strain 1 was x over L, now the E2 would be 2L, but since E1, epsilon 1 equals to epsilon 2, this means that this has to be twice the same extension. So twice the same extension would mean that if this was the old extension, same distance would be this. And since we are talking about the same force or same amount of stress, oh, sorry, no. Oh, my bad. This would come over here. So the D part is the one that makes the sense. Right, okay, moving on. The graph shows the variation with distance along the wave of the displacement of water particles at a particular instant in time for a transverse water wave. P, Q, and R show the positions of 3 water particles in the wave, or which of the particles has the greatest speed in the instant shown. So this is, if you're familiar with math, this is a sine graph. So we know that velocity or the rate of change of velocity is the rate of change of displacement. So the derivative of sine is cosine. So we know where displacement is highest, velocity would be 0. Where displacement is 0, velocity would be highest. This is also repeated in the simple harmonic motion chapter in A2 also. So where it's greatest speed, where you have maximum gradient particle R. Right, okay. Which phenomena is only associated with transverse wave? Polarization is the thing that is associated with strictly just transverse waves. So this is straightforward. Okay. A wave is displayed on an oscilloscope. Oscilloscope settings are time-based, 300 microseconds per division, Y gain 40 microvolts per division. What is the frequency of the wave? So to figure out the frequency, we need to know the time period. So let's take a point that we can measure the time period from. So for example, or what we can do, there's more than one thing to do. What we can do is we can measure points that are in phase. For example, this point appears to be in phase with this point and this point. So from this point to this point, 2 waves have passed. So from point 1 to point 3, 2 waves have passed. So 1 and 2. So if we can find out the distance between this point and this point, not this point and this point, let's call it point 2, we can figure this out. So 1, 2, 3, 4, 5, 6, 7. So, so time period is time base 300 microseconds per division times by 7 divisions. So 300 times by 7 is 2100 microseconds, or this is, you can write it as 2100 times by 10 raised to power minus 6. Frequency would be 1 divided by that. So 2100 times by 10 raised to power 6. This is 476. This is not correct. Wait a second. 1, 2, 3, 4, 5, 6, 7. Oh, sorry, my bad, my bad. We had to divide this by 2 also. We said there were 2 waves. So 21 divided by 2 over here, divided by 2. So 950, right? So roughly 950. So 26B. Okay, and an electromagnetic wave traveling in free space is not visible to the naked human eye. What is the possible wavelength of the wave? Not visible. Visible spectrum is in between 400 nanometers to 700 nanometers. So anything other than that will be part of that. Now, this is what we need to figure out uh, uh, to decode that. We need to decode that. So 4.5 10 raised to the power minus 10 kilometers. So in meters, this would be 4.5. 10 raised to the power minus 10 plus 3 is minus 7, which is 450 nanometers. So this is part of the visible spectrum. So this means that this is um, not the correct answer. Similarly, this is 620. Again, part of the visible spectrum, so no. 5.4, 10 raised to power minus 6 centimeter. So this would be 5.4, 10 raised to power minus 6, and then minus 2. This would be minus 8 meters. In nanometers, if we want to convert it, what we can do is, we know that to make it into minus 9, we have to um, divide by 10, and then we need to multiply by 10 over here. So this becomes 540 nanometers. Again, this is part of the visible spectrum. Now, everything, all first three are not part, so this means that this would be the correct. Now, what we can do to convert this, we know that to make it into 10 raised to power minus 9, we need to multiply by minus 1, and we need to multiply by 10 over here, making it 54 nanometers. So this is not part of the visible spectrum, so this means that this should be the correct answer. Okay, moving on quickly. Okay, electromagnetic waves of equal wavelengths are emitted from two sources X and Y. Waves are emitted from X and Y with a phase difference of 180 degrees. Detector moves along a path that is parallel to XY, detects a pattern of intensity, maxima, and minima. The diagram shows the arrangement of the sources and path of the detector. Intensity maximum is detected at point Z. Length xz is 70 centimeter. Length yz is 110 centimeter. What is the possible wavelength of the waves? Now, there is a very peculiar thing over here, that the phase difference is 180. Now, if the phase difference was 0 degrees, what would have happened is that constructive interference would have happened at even even multiples of half wavelengths, where n is even, and destructive interference would have happened at odd number of half wavelengths. However, the phase difference is already 180 degrees. So this means that the rules, these two, they will be reversed. So this time, the constructive interference will happen at odd multiples of half wavelengths, n are odd, and destructive interference will happen at even multiples of half wavelengths. So where n is even, sorry. So we according to the question, we have an intensity maximum. So at intensity maximum, this means that this is a constructive interference. So we are supposed to have odd multiple of half wavelength, right? So this means that we need to figure out, first off, what is the path difference. The path difference will come out to be, so path difference is basically odd multiple of half wavelength. So what we can do over here, so we know that this is 110 minus 70, and this is n over 2 lambda. N again is an odd number over here. So 110 minus 70 is 40 times by 2, 80. So 80 divided by some n is lambda. Again, n is supposed to be an odd number, not an even number. So if we get odd number over here, sorry, if n is an even number, for example 2, 4, if for example n is 2, let's give it a trial run. So if n is equal to 2, lambda will come out to be 40, right? However, if n was 1, it would have been 80. If n is 3, lambda would come out to be 80 divided by 3, 26.6. If n was 4, lambda would come out to be 80 divided by 4, 20. Again, we are not even considering them, but just to play around with this. N is equal to 5, 80 divided by 5. Now this is going to be interesting because, this is now going to be 60. As you can see, this is possible. So this wasn't possible, this wasn't possible, this is possible. So we're looking forward odd multiple of half wavelengths. And remember why we were actually doing that, because the phase difference between the sources was already 180 degrees. Okay, moving on. Two waves of the same type overlap. When does the principle of superposition apply? Okay, always. Only when the waves have the same amplitude. No. Only when the waves travel in opposite directions. No. The problem are the keywords over here. Only when the waves have the same frequency. No. This would apply always. If the waves are overlapping, the principle of superposition would apply. Okay. A ripple tank contains water at a constant depth. The water wave of constant frequency travels towards a gap in a barrier placed in the ripple tank. The gap is made smaller. Which diagram represents the wave before and after the barrier? Okay, so since we are making the slit width smaller, we're supposed to see more diffraction. So D would be the right answer. See, the size of this wavelength is almost approximately equal to this obstacle, also the slit width, so we should expect more diffraction. Light of a single frequency from two coherent sources interferes to produce a pattern of bright and dark fringes on a screen. Which change results in a larger fringe separation? So x is equal to we had lambda is equal to ax over d. Fringe separation is x, so that would be lambda d over a. Okay. Lambda is wavelength, d is the slit to screen distance, and a is basically the slit width. Increasing the distance between the sources and the screen. That is D. So yes, that would be correct. Increasing the distance between two sources, no. Increasing the frequency of the light, it will not have any effect. Actually, it would have, because you see, increasing the frequency would decrease the wavelength, so it would not be correct. Sorry. Increasing the intensity of the light. Intensity of the light will increase the brightness of the bright fringes. So A is correct. Okay. The current I in metallic conductor of cross-sectional area A is given by this formula. We are very familiar with this, where E is elementary charge, V is the mean drift velocity of the conduction electrons. What is represented by N? We already know this is the number density. Number density is number of electrons per unit volume. This is this. What cannot be the charge on a carrier? Okay, this is simple because charge is quantized, meaning that Q, any charge, is going to be some integer multiple of fundamental charge, where N is from integer number set. So if we divide each of them by E, which is 1.6, 10 raised to the power minus 19, if it is not an integer that comes out, if N does not come out to be an integer, that would be the possible answer. So let's see. So we have 4.8, 10 raised to power minus 19 divided by 1.6, 10 raised to power minus 19. So this is N is equal to 3. Oh. So this can be the charge. Then we have minus 3.2. That would also be giving us integer number. So N is equal to 2. That is still correct. Minus 2.4. This is going to be the odd one out, because you see the plus 3.2 will also give us N is equal to 2. This is going to be the only one that is giving us different number. 3 over 2, that means this cannot be true. Okay, moving on. A steel wire of length 2.2 meters is connected to a battery as shown. The reading on the voltmeter is 1.5 volts and the reading on the ammeter is 4.9. The resistivity of steel is this. What is the diameter of steel wire? Okay, so first off, we can find out the resistance. So resistance would be V over I. V is 1.5 divided by 4.9 amperes. So 1.5 volts divided by 4.9 ampere. This is going to be 15 over 49. We can keep it as that, or we can use the 0.306, also absolutely fine. This is ohms, by the way. Now we need the diameter. First off, we can find out the cross-sectional area. So we know resistance is equal to resistivity L over A. So first we can figure out A. A is rho L over R. Rho is given to be 6.9. 10 raised to power minus 7. Length is given as 2.2. And R we have just found out, 306. Okay, so this would be 6.9, 10 raised to power minus 7 times by 2.2 divided by answer. So this is going to be a very small number. So let's find the standard form of this. Area is 4.956, 10 raised to power minus 6 meter squared. Okay, now this is a circular wire, sorry, the circular cross section. So cross sectional area is pi d squared over 4. So d squared would be 4a over pi. So square root of 4 answer divided by pi. The answer would be 2.51, 10 raised to power minus 3. This would be the answer. Straightforward working. There's nothing more inside it. Okay, two resistors of resistance R and two resistors of resistance 3R are connected to a cell of EMF 8 volts as shown. The cell has negligible internal resistance. What is the reading on the voltmeter? Okay, so in questions like this, either we figure out the difference between voltages this way or potential differences this way, or just these ones. Let's call it 3 and 4. Not alternate ones, this way. Like they should be along the same positioning over here. So, for example, if we go the black way, we can see. So 3R over R basically means that the potential difference V1 would be 3R over 4R, because 3R plus R times by 8, which is going to be R times by R cancelled by R, 4 times by 2, 3 times by 2, 6. So V1 is 6. V2 on the other hand, that is going to be 1 over 4, because R over 4R, times by 8, so that is just 2. Now we basically have every idea now. So if this is 6, this is 2, this is going to be 6 volts, and this is going to be 2 volts. So the difference either way is going to come out to be 4. So V1 minus V2 is going to be 4 volts. Either way, over here, V4 minus V3. See, the reading on the voltmeter, we are only concerned with the positive value over here. So 6 minus 2, this is going to be 4 volts. So 4 volts, either way, is going to be the answer. A battery has an EMF E and internal resistance R. The battery delivers a current I to a variable resistor, and the potential difference across its terminals is V. The variable resistor is adjusted so that I increases. Why does the potential difference decrease? Okay, so V is basically the terminal potential difference. So terminal PD, this is equal to the EMF minus the lost volts. So this I times by, let's call it capital R, is equal to E minus I times by small r, because of the internal resistance. This is also written in this booklet over here, somewhere down below. See, lost volts EMF minus terminal potential difference. Now, why does V decrease? That means this thing is decreasing. This is decreasing. This would mean that the difference between E and IR is decreasing. So this means that IR is increasing. That means the current is increasing. If the current is increasing, now normally you would say that if R was a constant resistor, IR would increase if the current increases. But we already said that variable resistor has been adjusted. So if we decrease the variable resistor resistance, the current will increase. So if the current will increase, it will affect the lost volts. Lost volts will increase. The terminal potential difference would decrease. So EMF increases, no, EMF remains constant. Internal resistance R is also constant. potential difference across R increases. This is the only thing that is correct. So 36 is C. Okay. The electrical device of fixed resistance 20 ohms is connected in series with a variable resistor and a battery of EMF 16 volts, negligible internal resistance. The power dissipated in the electrical device is 4 volts. What is the resistance of the variable resistor? Okay, so power dissipated in the electrical device, P is equal to, let's say, I square R. Uh, this can tell us about the current flowing through it. So 4 volts divided by 20 is I squared, so 1 over 5. So I is basically square root of 1 divided by 5. So this is 0.4472. 4472. Now, if current is flowing this means that we can also find out the potential difference ratio between these two. So we know the current that is flowing. So V across device would be 0.4472 times by 20 times by 20, we get 8.944 equals, so 16 minus answer, that is 7 points. So the potential difference across this is 7.055 volts. So to find out the resistance, R is equal to V over I. V is 7.055, I flowing through it is 0.4472. So this divided by 0.4472, 15.7. This is roughly 16. So don't worry about this. We can convert it back to normal mode. This is 15.77, which is 60. So 16 is the answer. A nucleus decays by emitting a beta plus particle. Which particle must also be emitted from the nucleus? Okay, so in the beta plus decay, an electron neutrino is decayed with it, is released with it. So electron neutrino. Antineutrino is in the beta negative. What are the charges on an anti-down quark and an anti-strange quark? Okay, so just to show you the table, we don't have the table over here. Oh, we do have the table. Sorry, I forgot. My bad. So anti-down and what they say, anti-strange. Sorry, anti-down and anti-strange. So anti-down is 1/3. E and anti-strange is also 1/3. So that's it. 1/3, 1/3 E. Both are positive 1/3, 1/3. Now, how can you memorize this? We know that up, down, up, strange. Sorry, my bad. I mixed up the sequence. The up, charm, top have 2/3 E positive charge. That means down, strange, bottom have minus 1/3 E. Their anti quarks will have the opposite charge. Anti-up, anti-charm, anti-top will have minus 2/3 E charge, and anti-down, anti-strange, anti-bottom will have plus 1/3 each charge. So you can memorize it this way also. But it would be good if you just read the table for once. Okay. The nucleus of a radioactive isotope of an element emits alpha particle. Daughter nucleus then emits a beta negative particle, and the daughter nucleus of that reaction emits another beta negative particle. Which statement describes the final nuclide that is formed? Okay, so just to go overview of the what is happening over here, the beta particle, sorry, the alpha particle. Um, sorry, what was I saying? Yeah, okay, my bad. The alpha particle, it subtracts 4 from the parent mass number and minus 2 from the proton number. So this would be the daughter nucleus. Now, when a beta negative particle decays, so in beta negative, remember, neutron decays into a proton, and a beta negative and an anti neutrino. So this means that the proton number is increased, mass number remains the same, but proton number increases. So x, y, so a minus 4 remains the same, but the z minus 2 plus 1, this will become minus 1, basically. So this would become a minus 1. Furthermore, that happens another time beta particle happens. So the mass number remains the same. The proton number, sorry, the z would be get confused with that. Let's use a different uh, letter. Let's use S. Another time the proton number is added, so this would become the original proton number. So the mass number is same, but proton number will be the same. So if the proton number is the same, so it will be the isotope of original element, because isotopes are determined by are recognized by the same proton number. So it's a different isotope of the original element, and that A would be the answer. Now, this is the end. Now, this was the end. If you feel uh, any doubt, any confusion, feel free to reach out in the comments. If you feel I wasn't able to explain a certain question properly, also tell me that in the comments. I will try to explain that again. Please do check that out. The Grade Booster Pack, I will give that link. This is available on the Patreon. This I will give the link in the shop. This is the link actually. I will give the link in the description. Don't forget to check this out. This will be very invaluable help to you. Sorry, very valuable help to you. My bad. Okay. All right. Now, hopefully we'll see each other in the next video. Terribly sorry for being a little slow. I've been unwell, but I'll try to get back on track very soon. All right. Take care. Bye bye.